Let's collect those equations. So k squared is given by minus j omega epsilon, minus j omega mu, j omega epsilon plus sigma. That's the first equation, which gives us the square of the wave number. Now there is a second equation which says that the impedance is given by a square root of j omega mu divided by j omega epsilon plus sigma. And now this more or less describes the matter from the point of propagation and reflection of an electromagnetic wave. In fact, we are not able to directly measure those quantities. This is possible at low frequency if we make two parallel plates and those are absolutely conductive or much more conductive than the media we measure. We can then stick the measured material in between those two plates and measure the current that is caused by imposed voltage, and we can measure also the current or the displacement current, the capacity of that capacitor, and that would give us permittivity, and we are able to arrange similar magnetic measurements, and we can measure those values at DC. Now with increasing frequency this is no more possible, and in fact what we can measure is a reflection at the boundary and a transmission through some depth of the material. As the reflection has both a magnitude and phase, and the transmission has both damping, that is magnitude, and phase, we have four independent numbers to be achieved. Thus you would expect somehow to have four independent values in material description to be able to match for all of that. But surprisingly, for natural materials there are only three: permittivity, conductivity, permeability. Now, conductivity at DC means that there is a charge transport through the material, and we can measure a ratio between current and voltage, and given we know the shape of the sample, we can then establish conductivity or specific conductivity. But at high frequencies this is impossible. In fact, we use another approach. If you watch those two expressions, the material is lossless if there is no conductivity. So this conductivity, specific conductivity sigma, is found guilty for any losses. And in fact, you can't expect that this is really a charge transport. If you, for example, have a dielectric material and you start to polarize it with increasing frequency, then those domains, or molecules, or atoms, call it whatever, would have to repolarize. And the faster they do it, it can come to some resonant frequency at which there are a lot of collisions between those particles or parts, and that gives rise to heat. There are no currents flowing from one part to the other. That's just a collision of non-conductive parts. But the heat is a result which would be there if there was a real conductance. And we find out those parameters, mu, epsilon, and sigma, so that they fit both situations. They give us good predictions of transmission, they give us good predictions of reflection, and this is enough. So these engineering parameters for high frequencies, in fact, are measured using transmission and reflection, and they give us good prediction of transmission and reflection, and that's all. But there is one important exception which is not found in the nature, but there are materials we artificially create for a special purpose. And this is a problem that has dual applications. That is, there are applications for protecting or damping signals at, for example, airports, and there are applications in military. I start with those first ones. Just imagine you have a radio locator. So you have an apparatus that has a transmitter connected to an antenna. It radiates a wave, and the wave reflects back, and let's say we have a bistatic, so we have another antenna that collects the reflected signal and gets it to the receiver, and after evaluation you can see the aircraft flying in some vicinity of the airport. Now this seems to be very simple, but it's the same problem like if you have a torch at night and you try to see something which is distant. The rays are diverting, and the intensity of illumination with a torch or with a radio locator decreases quadratically with distance. If you radiate 1 kilowatt of power, it covers, let's say, 1 meter square in the vicinity of the radio locator, and the farther you go, the bigger area it is spread on, and therefore the power decreases quadratically with distance. Now there is a reflection, and the same thing occurs on the way back. So the power that you receive from a target, be that a radio locator in a plane or a dog and your torch at night, is inversely proportional to the fourth power of the distance. Now imagine that you want, for example, to have a long-range radar which covers 1000 kilometers. Then it means that the power that returns back is extremely small, and you would have to compete with this fourth power law in two possible ways. First, you can increase the power of your transmitter so that radio locators easily do have megawatt powers. They radiate it only for a short portion of time, so that the average power is not that bad, and it will not bake you if you were around. But anyway, you could raise the power, and you should have a very, very sensitive receiver, which is very nice. But what if you have sent the pulse, which has a 1 megawatt, and it did not reflect at a plane somewhere at the Mediterranean Sea, but it reflected 100 meters from your antenna. For example, if you are at the airport, you still have planes that are at the airport. You have their cars, you have their buildings, people, and all those reflect. So you can get a reflection which traveled for 1,000,000 times shorter distance. That would have the power raised to fourth power, so it would have 20 orders of magnitude higher power. And if you have a sensitive receiver, you could damage it easily. So you have to protect it, and the protection for this big differential in magnitudes must be multi-layer, multi-means should be used, and one of them is causing things that are in the vicinity of the transmitter not to reflect waves. So you would need something that would cover the surface and stop reflection. The same problem is in military. You have planes that do not reflect in order to not be seen by radio locators. You have ships that are protected not to reflect, and the same thing could be done possibly by some material that you will spray on the surface, and that material should have two important properties. So we have a metallic surface, and a metal by its nature has zero or very small impedance, so it causes a total reflection. So you have a metal, and then you have something on that, and that something should first not reflect here, and it should damp the signal, so after it comes to the metal it's already damped, so there will be no reflection. What nice, but the problem is that to have damping in the material, you need the conductivity to be distinct from zero. If it's zero, it does not damp. Then you need the surface of this sprayed material to have no reflection, which means that the reflection which is given by so ideally you should have the wave impedances of this material and the air identical. But the problem is that the impedance is given by a square root of j omega mu over j omega epsilon plus sigma. And now if you have there a non-zero conductivity, you get losses, but this number is complex. You have a real nominator and a complex denominator. This number is always complex. Then you can't ever get here a zero reflection coefficient. So then you have a problem. If you increase losses, well, then the signal would be damped by reaching this metallic surface, but it would already reflect from this surface. So what's the achievement? Unless you find out a material that has both magnetic and dielectric losses. But then you have to have also something which is denoted by the same letter like specific conductivity, but the dimension of this is inverse. And those special materials are provided by chemical technologies and could do special coatings that do not reflect, at least in some frequency band. They do not reflect. Once you provide this to have the same impedance like vacuum or air, you could achieve good damping of surfaces. This is quite investigated and handled by military services. This also could be a powder that is just sprayed to the air so that you can't see inside that cloud by any radio locator and so on. So this is something which is mostly used for special technologies, and I have noted it because you are becoming engineers and you should know the topic, but this is the only mention I'm doing in this subject. For other purposes, we are going to forget for magnetic losses, and we have only mu, epsilon, and sigma as a full characterization of material that is necessary to handle electromagnetic wave problems. Ladies and gentlemen, your questions, please. Well, if there are no questions, both you and me have the right for a 5 minutes break.